message showing a URL. If you click it, you get a virus. I'm just kidding. So those are videos from the first class. Okay? Especially you missed the previous class, or you forgot about something when I was explaining what you need to do to satisfy all the course requirements. What are the coursework, the grading elements? What are those? Those are all in the first video. So I just divided the whole class into 3. So you can review that to remind yourself. I've received several questions regarding the online discussion part. So what you all need to do is, by the way, if you want to keep watching this video later on, I recommend you to download this, because I will probably have to delete this. It's free Google Drive. If the storage fills up, then I have to delete something. So I cannot guarantee how long I can have this on the web page available. On the same content page, no, it's not content, discussions page, the second form, topic discussion, has a bunch of discussion boards with numbers from number 1 to number 40. Yeah. So what you're gonna do is, I will set a date and time, and just go over this list and see what are the topics that you are interested and want to try. And as soon as I open another discussion board, you have to write your name. Hold on, no, that's the old way. If you like this topic, then you need to write your name or write something. It can be just a single dot as a placeholder. If you don't write anything, you cannot save it. So just click write, which it doesn't exist now. You cannot write anything yet. But as soon as I open this discussion board, then you will be able to write it. So go to the topic that you want, write something, then whoever write or leave a message on that topic first will be the owner of the topic. Okay. That's how you secure the topic for yourself.
Do you have a date set yet?
Not yet.
Okay.
I'm still debating whether I should do this before or after the first exam, because before first exam you have to cover lots of different topics. That doesn't mean the second part is not any easier, but at least you can have more time to spare. So we'll see. So once you secure the topic for yourself, then you go out and search some information, relevant information about that topic, and summarize them in a document. It can be a Word document, it can be a PowerPoint slide, whichever document that you can make use of it for your later presentation. So that will be the first part of the online discussion. What else you need to do for that online discussion category? Go back to the first video and watch that part that I planned it. So these are the things that you should be able to see on my Google Plus page. So the latest post that I made, this one, I posted this FBI honor internship program 3 days ago. So if you added me, if you start to follow me up to today, you should be able to see this message.
What message is it?
This is about FBI internship.
I do not see it.
Did you add me on your Google Plus?
I'm looking at your Google Plus, I don't see it. The most recent one I see is January 26th.
And you don't see this?
No, sir.
Someone else? You can? Alright, then it's likely that I didn't add her in the right bucket. I have added 22 students so far. What's your name?
Tamara, T-A-M.
Oh, yeah, I know that you have some issues. Did you get my Google Hangouts message?
Let's see.
So I know that a couple of students still have problem connecting me on Hangouts. So I sent my message, I sent the Hangouts message back. So if you can see that, then we are connected. Then I know that one of the students had privacy setting that this allows me to add the student.
I do see your message. Okay,
Is
go
that
ahead.
you?
I will.
And also I have 2 or 3 connection requests, but those names are, I couldn't find those names in my student list, so I just didn't add. It's not only about privacy or marketing annoyance, but when I have student group, I don't want to have, I have a bunch of ships and I don't want to add a wolf in the group. So I guess that also make you, feel easy to be included in my group. So if you have sent something to me, whether it's a Google Hangout, Google Plus connection request or Hangouts message, and your name is something that I cannot identify, then you need to send me an additional message. So those with this follow category are the ones who connected me, but I didn't add them to any group yet. So I couldn't identify. Do you have a CJS? Maybe from other class.
I saw a friend of mine on there who graduated a couple years ago.
There are some cases where who start my class but drop. So I didn't want to add more junk when I'm keep posting something relevant to my class, and if it's not in my class, then
I can give you his name if you want to remove him.
I cannot remove the follower.
Oh,
It's
okay.
up to him or her.
Okay,
But I don't add him to my group, so he cannot see anything that I post.
understood.
Or some friends from Korea. He's not my student, so yes, no business. This one is also new. Dr. Rina Bites. Alias. Do you have anyone? This alias in this class? This class. Troy. We have Troy here. Right. So you now you know, I have some people who I couldn't add to any group because I couldn't identify which group they belong. So if you don't see this circle string, you should be able to read this. If you don't see this, then you are not added to the right group. So send me a message or email. If you cannot access, you cannot connect me on Hangouts, then send me an email with your Google Gmail account that you use for your Hangouts. Then I can add you from my end, and that usually solve the problem. In the other course that I'm teaching this semester, which is also about networking, that's for graduate only, a student asked a question about the topic that I covered in the first class, and then I answered with group Hangouts and asked him to post it on the group, on this discussion board. So if you have any question, if you have a question during the class hour, just raise your hand and ask. While you review the content by yourself and have a question, have a doubt about what I explained, then you can send me a Hangout or post a question here. If there's topic-related question that I covered, I prefer to have the question posted here. That way, other students can share your question and answers. Okay? If you send me a Hangout, that's fine, but I will probably ask you to copy and paste it on the discussion board after I give you an answer. Right, network models. So in this chapter, let me turn this light off. Don't fall asleep. We'll talk about the network architecture and the network architecture that is reflected on the reference models, where we will cover two different types of reference models. One is OSI 7-layer model, the other one is TCP/IP 5-layer model. Then we will discuss why we need them, how to use them, what are the concepts in the models that you need to understand and remember, how they work, and what are the devices that you can expect in each of those layers. So how many of you have learned or saw one of those models even briefly, very, very briefly in your past? Okay. A few. All right, that's fine. So reference models, so this is an example of reference model. Beautiful, isn't it? You have 7 boxes, not only 6, not only 8, exactly 7 boxes. And there's a word in it, yeah? Nice. And there's another model that has only 5 boxes. Believe it or not, these are the second one is more important in this course. You got to remember inside and out, and have to have very clear understanding of these boxes, their functions, their role, their interactions at the end of the semester. Okay? So these are very, very important models, although they don't look very sophisticated or fancy. Those are called network reference models. And if you think about the whole process of data communication, we are talking about 2 devices, electronic devices. It can be a cell phone, it can be your laptop. you want to communicate with someone else somewhere on the internet, you don't know where, and you expect that your device in your hand will talk to the device the other person has. You don't know the brand, you don't know the model of the device, and somehow you are naturally expecting that you can talk over the phone, over the device, right? It won't be possible if we don't have those reference models, because every device manufacturers will come up with their own best solution that may work beautifully between their own products, but when it comes to interoperability, you cannot guarantee that your device that you develop is gonna talk to another device. And it's global scale. Okay? You may not have heard of the brand of the device manufacturer. Okay? Even the what's the name of those Chinese cell phone company? I heard that they actually work better than the latest Samsung on some aspects. And I haven't heard of those names until a few years back. Right? But now they are working fine. They run all the software. They talk to any device on the internet and things like that. Because everyone follow the same reference model when they develop their product. So whether you use OSI 7-layer model or TCP/IP 5-layer models, if you follow the same reference model as all the others, you can guarantee that your product will work. So that means the primary purpose of this reference model is to make sure anyone playing in the market meet all the requirements that will automatically make their product work with others' product. So how they come up with this reference model? So a bunch of engineers come together and think about all the possible steps that your communication device will need to have successful communication. List down all those things. It can be hundreds or thousands of little nitty-gritty details. And then group them again in the right order. What needs to be done first, what needs to be done second. Maybe third and fourth may just don't really need the order, but they have to be done within a time window or within the same device. So you list all of these and group them into coherent subgroups, and then put them in the same box and come up with this different number of boxes. Some can come up with seven boxes, some came up with 5 boxes, some came up with 4 boxes. And they all agreed at the end of the day to go with this particular reference model. So in theory, some function can be done here or there, but as long as you agree to follow a certain model, then everyone developing a product that works in that layer will provide those functions, not other places, and they will automatically make their device to work well with another device that follow the same model but designed in a different layer. So, for example, if you have a laptop computer, well, a desktop computer, how many of you still have desktop? Okay, quite a few. How many of you have plugged in any extension card in it? So in case you have never opened your box, if you open the box, this thing, the boxy box, you may see some slots where you can plug in some cards. Here are some samples. Pass this around. These are the second generation Ethernet cards. So you can plug that into the slot and your computer will instantly start to use the device that serves all the functions that should be taken care of in the first and the second layer. By the way, when you see a reference model, there are numbers, and always the small number starts with the bottom layer. Okay? So layer 1, 2, 3, 4, 5, or 1 all the way up to 7, depending on which layer, which model you look at. And what else do you have in your computer? Your operating system. Okay? Your operating system these days, unless you somehow keep the Microsoft DOS from like the 80s or 70s, they don't have network component. But these days, all operating systems include networking components, and those do not include these two, because then there will be conflict. These two are included in those cards, and you cannot have another one, which will fight. But every operating system will have network layer and transport layer modules, and some application layer modules included in their operating system, and nicely interface with any network device that meets this standard. So, OSI 7-layer model is standardized by what? We briefly talked about that. ISO, yes. ISO standardized OSI 7-layer model. And it starts from the first layer, bottom layer, physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. I speed up the last three intentionally because it's important to know that there are three of those layers above transport layer, but then they just combine into one single application layer in TCP/IP protocol suite. The original TCP/IP, or you can call it Internet protocol suite or Internet network layer, network reference model, did not have separate data link and physical layer in the beginning. It just had a link layer. But then later on, to make it more easy to understand and standard and comparable with the previous OSI 7-layer model, they just divided into physical and data link layer. So we have now 5-layer model. So this is not the original, but this is more widely used reference model. So from physical layer, layer 1, data link, network, transport, and application layer. And as long as you have all these session, presentation, and application layer functions in a single product, then they will work with other product that follows this TCP layer model, because there's a nice interface between transport and the application. These are some examples of, so first you have mapping between 7-layer model here in the gray, and then 5-layer model, and then some examples of protocols and products. Let's start from the bottom, where you have physical layer and data link layer. So physical layer is where you actually generate signals. So the digital data that your computer creates, ones and zeros, will convert to the electromagnetic signals. It can be light signal or anything. It can be ultrasonic, although that's not very conventional. So that's where the signal generates and travels through the medium. And then you have data link layer. That's where the actual message consists of ones and zeros will be created. That's where actual ones and zeros are written and wrapped in a nice package that actually travel, converted to a signal and travel through the network. Okay? And those are usually those come in a package like this network card that I just ran along. They include the physical layer, which include the port and the signal generator, and then the software that creates those message unit. Because they are so closely related, they usually come in a single package, like a single card. Where is the software part? It's in the chip. It's hard-coded on the chip. And then you have IP, so you have big IP. Why is it that big, much bigger than the other boxes? Because it's most important in these days, networking. If you want to use the internet, IP stands for what? Internet protocol. Without IP, you cannot use the internet. No matter what you do, you got to use IP. And then you have two little boxes here, two little boxes there. The thing is, every time you go up to the higher layer, they are the user of the service provided by the lower layer. At the end, at the top, above the fifth layer, what do you have? User, yes. So you have user, either human user or robot or other software. There's a user that uses application service. And that application, which usually will be software of some sort, will use the service from transport layer protocols. And then transport layer protocol will use the service from the network layer protocols, which will actually create a message format that can be delivered over multiple networks across the whole internet. And then, oh, by the way, the IP, one of the functions that IP does is to create message format called IP packet. Right? Everyone heard about IP packet. Don't be confused. You don't see IP packet if you can see what's going on in this air. You have Wi-Fi signals going around, and you can read ones and zeros and try to find IP. You cannot find it because it's wrapped inside of another message. It's like you write a message and you folded it, but you cannot just send it to USPS. You have to have a nice standard envelope, right? And then address it. So you cannot read the actual message, the page itself, but you can only see the envelope, which follow all the standard, and that's created in the data link layer. So even IP use service from data link layer. And then data link layer use the service from physical layer, which is signal generation and conversion. So data to signal, signal back to data. And then why do you have this small box? Some are in the lower half and some on the upper half. Because IP need to use these two to work properly. But these two, so these are all in the same box, the network layer box. But these two do not need IP. They serve for IP, but IP do not rely on, hold on. And so they do not rely on IP. ARP and ARP means reversed ARP, create its own message that will go down to the data link layer by itself rather than going through IP. So these are some exceptions that can travel through, that can use the data link layer protocol without IP's help. The other two over there, they are upper half, in the upper half, and ICMP, IGMP creates its own message, but they have to ask IP to carry that message inside of IP. So there are little difference. These two do not rely on IP delivery. Those two rely on IP delivery. And all the others above it, TCP, UDP, SCTP, they all rely on IP for delivery. And then the application layer protocols rely on transport layer protocols. And then they are also included in the IP as well. So you cannot jump from layer 5 to layer 3. You have to go through each and every layer, relying on each other. So the lower layer protocols provide service for the upper layer protocols. So we already know that data link layer create the actual message unit that will travel through the network, the medium. Then what's network layer for? move a packet. So IP packet is created in network layer by IP, and move it from source to destination, where the source is a computer on one network, and destination is another computer on another network. So without IP, your computer can talk to another computer on the same network. So when I first developed the network in 1993 using one of those network cards, those are actually from that time, ended up in my closet. There's no such thing as internet. Well, maybe there are some, but I was not aware of that thing. And all the device computers, desktop computers that are interconnected are on the same network within a single LAN. They talk to each other fine, but I couldn't make any of those computers to communicate with any other computer outside of those LAN because we didn't have IP then. So IP is for communication between source and destination, which can be scattered around and any place within on the internet, which consists of multiple computers and multiple networks, hundreds and hundreds of networks on the internet. The transport layer is like a supervisor. Okay? So IP is pretty chaotic protocol. How many of you watched the video that I recommended? If you haven't, maybe I should play it during the break time, but watch it. That will give you a rough idea. That will help you a lot if you are new to this area. That will help a lot to grasp the idea in the beginning. So IP is important and widely used, but it's not reliable at all. You will learn more about it, but it's like one of the most unreliable friend. And you are asking the friend to do certain very important thing, deliver very important stuff, big money to someone that you have to pass the money. And the chance is that guy, or whoever the person is, will lose it and will not be responsible for it. So you have to have an additional layer of protection. So like another reliable friend, just following, shadowing him all the way to that person whom you have to pass the money to. So that's transport layer. And then application layer is where actually the content of the user is received or created. So transport layer, network layer, data link layer, and physical layer all serve for the user who is using application layer modules. Going back to the physical layer, the bottom layer, ones and zeros are converted to signal, and the signal back to ones and zeros on the receiver side. So destination, source, and source has ones and zeros. And who made that? Where is that ones and zero from?
The data link?
Data link, yes. The upper layer of physical layer is data link layer. So data link layer is responsible for making this nice message unit, okay? And that will be converted to signal back to ones and zeros after the delivery. And data link layer, again, one of the most important function is to create this message unit. And that message unit is called frame. So if you have an Ethernet, as we all have here, Ethernet frame. Wi-Fi frame. So frames are the message unit that actually travel through the medium. And the frame structure can differ from protocol to protocol, but both the two most widely used network LAN protocols are the Ethernet and Wi-Fi, right? And both of them have header and trailer. In the header, you put the additional information about the data being carried. So the sender put the header, receiver read the header and process the data as the header indicates. And the trailer is usually just redundant bits to check, to allow the receiver to check whether there was an error in the data or not. So the data link layer protocol will determine how long a frame can be, what's the size of the header, what's the maximum size of the data, how many fields you have in the header, what each of those header fields mean, and how to process them. So with the bottom two layers, the physical layer and data link layer, you have a network, or a link, one link. You cannot have multiple networks interconnected with the bottom two layers. If you have only bottom two layers implemented, then you cannot interconnect the networks, but you can still have a single network where multiple computers are connected. That was the form of the network that I first implemented. And as you can see here, each device uses the bottom two layers of functionality. That's enough. You can have some connecting devices as well as the terminal device. But those connecting devices are also two-layer devices, and they do not separate a network into multiple networks. They just forward the frames back and forth, but they cannot divide, they cannot put any wall between different sections of the network. Still, you are looking at a single network. Everyone is using the same bottom two layer protocols. So here you see hop-to-hop delivery. That's the concept of a signal generated by a device, travels through a link or segment of the network, and received by this connecting device. So there, physical layer of this device will read the signal, convert it to ones and zeros, okay, and then repeat, okay, regenerate the same signal on the other side, okay, which will be exactly the same as the original frame, and pass it to the next intermediary. And that will receive the signal again, convert it to ones and zeros, and then regenerate the signal, and then pass it along. Why would you do that? Well, there's no filtering going on here. There's no division. And other than repeating the same message again and again, the intermediaries do not provide any additional service. So in the olden days where we had these intermediaries, which was called the hubs, we had them to have multiple ports so you can connect more computers. So that's one reason to provide a connection point. We have a bunch of ports on the hub, and you can plug more computers to that port. Second, you have the distance limitation for travel, signal travel. So if you generate a signal from a computer that can go, let's say, up to 500 meters, but not anymore, that you will see a significant signal deterioration, so you cannot understand the signal when you receive it. So before you hit the maximum distance, you put these intermediaries, and they are repeaters that read. So you can call it repeaters, but the actual function they do is regenerator. To receive signal from one port, understand whether they are ones and zeros, it's relatively easy, right? It's not analog, it's 1 or 0. And according to that interpretation, you regenerate the exact ones and zero signals again, and that signal will be as clean and good as the original. Okay? Because we are talking about digital here. So you can increase the maximum distance of communication partners as long as you can put more intermediaries. The computers are nodes, and all the intermediaries are second and two-layer device, which include physical layer and data link layer. And those different sections of the network are called segments. Okay? You can have multiple segments, so you have one segment, another segment, another segment, and another segment. So you have 5 segments of the network, but you are still looking at a single network with multiple segments. So intermediaries do not block or change anything. If the computer A sends something to computer F, it's a single hop distance, although it was relayed by multiple intermediaries. So what A generated is exactly the same as what F receives. Obviously, if you want to deliver something, you want to address the receiver. And in most cases, you also want to say who is the sender, just in case something goes wrong and the receiver or intermediary needs to contact back. So you use address, so you put source address and destination address in the header of the frame. So this box we are looking at here shows a frame, because we are now talking about data link layer. So data link layer, frame. So you have header fields, and obviously there are more than address fields. Okay? And how many fields you have in the header, that depends on the protocol. Ethernet is relatively simpler than Wi-Fi. Then you have data field, and then trailer, which is error checking field. The type of address that you use inside of this frame header is called physical address or MAC address. What kind of address are you most familiar with in data communication? IP address. So IP, we haven't talked about IP yet, right? Here in data link layer. So data link layer process have no clue how to handle IP. They just use MAC address. So it's like USPS. If you send a letter to someone in a different country, so across the border of your network, across the border of USPS network, then you have to use the international address. Okay? When you ask your mailman or mailwoman, can you deliver this place, which is like in Canada or South America or somewhere in Australia, they have no clue where that is and how to deliver that letter all the way over there. Okay? So they don't need to know the IP address, but they need to know where to take that mail. That's their local delivery place, like a local postal office or the distribution center. So as long as the driver knows where to take the message to, that's fine. Those are MAC address. And the MAC address, the scope of the MAC address is a single network. So last week, someone asked if you can have duplicate MAC address on the internet. Yes. Theoretically, you can have the same street address in different state, right? So because usually states are covered by different USPS office. So having a duplicate doesn't matter. But within a single network, you cannot have the same MAC address. That's good enough for this data link layer scope. But if you want to send your mail across the border, whether the border is state line or national border, and you're above the network boundary, you need something in addition. So that's where you have network layer comes in. And network layer creates this message, hey, that looks just like the previous box, right? Except for no trailer, yes. So IP create a message unit called IP packet. And IP packet does not include trailer. Well, at least IPv4 and IPv6 protocols do not include trailer, but they have header. So what happens on the sender side, you receive something that goes into data field of IP packet. IP process running on your computer will add some information in the header and send the whole IP packet down to the lower layer, where data link layer is waiting for. And the whole thing will be included in the data field here. So the whole IP packet will be included in this data field, and then the data link layer will add the header and the trailer if we send it down to the transport layer, and a physical layer. And when the receiver receives a frame, so first the physical layer will convert the signal back to ones and zeros, which will represent a single frame. And then data link layer will read the header of the frame, take out the data, pass it up, and that's what you have here in the packet. And then IP module on the receiver side will read through the header, understand what to do with this data, and pass it up to the upper layer. And now, because we are talking about network layer, IP, you can deliver a message from one network to another across many networks. So here, intermediaries represent a 3-layer device. Each of these disks that with big X represent 3-layer device, meaning that wherever you have this 3-layer device, 3-layer intermediary, that shows the end of a network and beginning of another network. Okay? So here you have one network on the left side, 2 networks on the right side of this intermediary B. You have one network connected to E on the left side and another network connected to the right side of E, etc., etc. So each link, so you have five links here. Each link shows different links. Now you see 5 different networks, or 5 different links, interconnected by three-layer. It's confusing. Three-layer devices.
I've got a question.
Yes.
So is this a similar model that would be like on a corporate intranet?
If you have very big corporate network, yes. The thing is, whenever you introduce a 3-layer device, you have additional bugs, right? So signal goes up here, converted to ones and zeros, processed, and regenerated. So this additional bugs, whenever you have additional bugs, it adds time. So within a single corporation, they prefer not to have 3-layer device. There are some high-end 2-layer device, well, it can still have some 3-layer functionality, but they can exclude the typical IP processing, but expedite the handling of frames in the data link layer. But rather, you can think of a whole internet. Whole internet is structured like this. So you have one network with a router that interconnects their network to another. Different companies are connected to multiple routers across the whole internet. If you think about the OSU Tulsa or OSU Stillwater size of the company, yes, they have multiple routers. For example, like in Stillwater, they would have 20 or some routers across the whole campus. Here, we may have a couple of routers per buildings. But if we just think about smaller companies or smaller footprint on the IT area, then they may have only one network with multiple layer 2 switches. Yes?
So each one of those links there if I run traceroute,
Mhm.
each return would represent one of those links.
Yes, if you send the trace route A to F, we'll talk about trace route later, but there's a special command that sends out specially designed packets, and your target is F. So every trace route message will try to go to F, but on each and every router, they are designed to return a message showing the IP address of this, IP address of this, and then IP address of the last. So yes, those are separate networks, and each delivery from, so where's my mouse? Even these nodes, the intermediaries are nodes on the internet. Routers basically are computers. Although they don't generate user message, they act like all the other device on the internet. So one hop is from A to B, not from A to F. Make one hop from here to there, and then this router regenerates the same the frame, a new frame, and then will travel through this link here, down here, and that's another hop, and then this router will regenerate the signal, which will be delivered to the final destination. So you have 3 hops here, from A to F. Does it make sense? So although they look exactly the same, if these intermediary systems are 2-layer device, you are looking at a single network. If those intermediaries are 3-layer device, then you are looking at separate networks. This doesn't tell this one. This picture shows 3 networks. Actually, you are looking at 5 networks. Every yellow oval represents a single network. So you have 5 networks interconnected. So this is another representation of interconnected networks. So at the top, so if you understand that this symbol, this pretty common conventional symbol, have a disk or oval with a big X on it, usually red color with white X. They represent 3-layer device. And wherever you see it, that's the end of one network and beginning of another. So you have one network up there, you have a router that punctuates the first network, and then a new network starts. And here you have another router. That means that's the end of this network, and then a new network starts. So you are looking at 3 different networks interconnected, and each network can follow different physical and data link layer standards. So first one looks like some kind of bus topology network, original Ethernet, and we have ring topology. That means it's different from the first one, and then you have bus network again in the third. And you see the boxes. Let's see what you have in the header. Okay. Well, so the big box represent a frame, and then the numbers, the 2 numbers in the light blue header represent the MAC address. Then what are those alphabet letters in the green box? It's inside of the data field of the frame, right? So what do you have in the data frame, a data field of the frame? A message from somewhere. So you have data link layer frame that has header part and data field part. Inside of data field, what do they carry?
Binary.
It's binary, but where do you get it? What kind of message is that?
Internet.
the data field. Let me draw a picture. So now we are looking at a frame. Who made this? What layer? Data link. Data link layer frame that usually have header, data, and trailer part. What would you have in the data field? And where would that come from?
Bits.
Everything consists of bits. Network layer, right? So in the network layer, usually you have IP. It's the big pattern of data link layer frame. So IP message will be received from the upper layer, which is network layer. So IP message will be received and then IP packet, which is called a packet, network layer IP packet, include header and data. So the whole IP packet will be included in the data field. That process is called encapsulation. Okay. Whatever the upper layer gives you, that will be encapsulated inside of the data field of the lower layer message. So inside of the frame header, you have source and destination address. And what kind of address are they?
Local.
MAC address, right? Data link layer MAC address. Inside of the data field, you have a whole IP packet. And the whole IP packet must have a header of its own. And inside of the header, it has its own address. What kind of address do you think IP use? IP address. So the first part of the data from data link layer perspective is the IP header, and where you have source and destination IP address. That's what you see in these big little boxes. You have MAC address in the outermost box, and the inside of the data field, which is white in white color, you have little two boxes that indicates the encapsulated header field of the IP packet. So A and P represent the IP address of the source and destination. Okay? A, IP address, P is also IP address. 10, 20 represent the MAC address of the source and the MAC address of the receiver, which is not right? Is that an error?
No, it goes to the link.
Do you see that number?
Mm-hmm. The pink circle, the top one.
20 is here, right? Destination is here, the first intermediary, the router. Okay. Because the LAN, the network, that data link layer level within a single network, no one understands IP. Okay? Data link layer cannot understand IP. So the source and destination must be within the same domain, within its own scope. So within a single network, so MAC address of the intermediary who will take care of all the outbound mails will be the MAC address plugged in the frame. MAC address in all the outbound messages. Okay. If this guy is sending something to this guy, then why bother? You don't need this guy. You can just plug in 87 here, and then the frame will be delivered from source to destination directly. But only if you want to send something out to the outside world, to the internet, then you have to address all your frame to the router. And that's one reason that router in this example is called gateway. So it's like a USPS sorting station that collects all the letters going to another country. That's where all the letters will be collected and then passed to the next carrier, another country's postal service. What happens to the message here? This router will read the source and MAC address, source and destination MAC address, and realize, hey, this frame was addressed to myself. So this is for me. And then go on and keep reading the IP addresses. And all the routers know how to forward an IP packet. So when it reads the IP header, it says, hey, destination is P, IP address P must be on this side. So I have to forward the IP packet down to this next hop, but that's not directly connected to the next network, so I have to contact the next intermediary to forward the packet to the next segment. Okay? And just like all the other layer 2 device, it will regenerate the data link layer frame. So this big box is totally new. You're not reusing this thing. Okay? You still have the same IP packet. That doesn't change anything, but the frame that actually encapsulates the IP packet is totally new. According to the new standard in this new second network, so the router will create the new header with its own MAC address as the source MAC address, and the destination MAC address is the MAC address of the next intermediary. So that message will be directly delivered to the next router. The next router will do the same thing. Read the MAC address and realize, hey, this message is for me. I can keep reading. So what's the destination IP address? P. Where is P? You look up its own kind of note, and that says, hey, P is an IP address directly connected to its own network on the lower side. So I can just create another frame here that goes directly to P, then the whole delivery will be completed. So it regenerates a frame with the same old IP packet, nothing changed here in the network layer, but the data link layer header is totally new. Okay? From 9933, we have 95, 63, 66. So this is totally new frame with new MAC addresses. So 66 is here, the sender's MAC address. 95 is the MAC address of the final destination. Okay. So it's cumbersome, okay? But for the electric devices who does not allow any room for interpretation or subjective understanding, this is the clearest way to make the inner connection of the network happen. So as you can see, IP does very, very important role. Provide the universal address any router can understand and find the right way to forward. But they cannot be delivered without data link layer's help. Data link layer is the actual layer that actually creates the message delivered within each of those networks and use the MAC address to make the final delivery, actual delivery. IP addresses are not used for actual delivery. The street addresses that you have to put on your letters or goods are actually MAC address. Without MAC address, the delivery cannot happen. Any questions so far? Then what do the transport layer protocols do? So the delivery is taken care of. Okay? when delivery has been taken care of, you need to provide some kind of reliability and traffic control within a computer. So on your cell phone, with a tiny cell phone, how many network processes are going on usually? You'll be surprised if you find out that at least dozens of network processes listening to the network, using the network at the same time. Okay? Your browsers are running, your Android, or what's, iOS. That's a great time. So whether you use Android or iPhone, they exfiltrate your personal private information to the vendor in a, under the name of customer relationship or something. So there will be some process going on to send your personal data, where you are, what kind of resources are used by what process and things like that. Those are constantly sent out. And then in addition to that, you call telephone. Even the telephone use IP process these days. Then you have Hangouts, you have Google Plus, constantly checking updates, and all those things use the network. That means all use IP module. You need IP process that serves each and every service in the application layer. How many IP modules and how many IP processes you have? One, yes. Each device has only one IP process. So to provide network service for those dozens of application processes that all want to use network, someone has to stand and put them in the right order before they break a big fight. So network layer, transport layer protocol, whatever transport layer protocol you use, must kind of interface multiple application layer processes with a single unique IP process, and put them in a single nice line and let them use it, take a turn to use the unique resource in the lower layer. And this process is called multiplexing, which will make you confused because there's another chapter where you learn multiplexing in totally different meaning. Just keep that in your mind. Keep in mind that in networking area, it's not uncommon to see the same term is used in totally different contexts, and multiplexing is one of them. Multiplexing here, when you are talking about transport layer, is the process of putting the application layer queues in a line and let them take a turn to use a single IP process. And the scope of the delivery in the transport layer is from a process on the source computer to the destination process, the final receiver process on the destination computer. So IP has to be understood and taken care of by each and every intermediary, as well as the sender and the receiver. But for transport layer protocols, they don't care what happens in the middle. They don't care what routers do. Routers are a 3-layer process, which means they don't have fourth layer, which is transport layer. They don't need to understand, and they don't want to. You don't want them to get involved in transport layer process. And transport layer process will connect one process to another on the source and the destination. So that's why even when you have multiple browsers popped up on your screen, you have one Firefox, one IE, and you have multiple tabs on each of those browsers, still you get the right response for each page, each tab, without having them all mixed up. Because transport layer will split the process and let them communicate with the right communication partner and handle all those traffic control kind of job. Any questions so far? Let's take 6-minute break.